Well, good morning, everybody. Welcome back. How was the 4-day weekend? Yeah? Wasn't a weekend, Mr. Balogh. I had to work the whole time. Yeah, I remember those days as a student. You can break out. You can find a standard 5-day work week. Happy Lunar New Year. That starts today. We'll have, let's see, what's going on this week? Chapter 6 is happening this week, and I failed to check the lab. What lab? Lab 5. Okay, yes. So tomorrow's lab, we are going to be doing Newton's second law on inclined planes. And so hopefully that's going to help cement a lot of that stuff with the free body diagrams and things like that we were doing. Hopefully that's going to help there, because I know that that's a spot where everybody always feels like they don't know what they're doing. And then Ramadan starts tomorrow. Ramadan Mubarak. And then, next week is a test. Next week is a test. Let's see, we've got, was chapter 5 due this weekend?
It's due tomorrow.
Due tomorrow, right? I moved those? Good. That was smart pass, Mr. Balogh. And then, what is it? Chapter 6 is due next Wednesday. Yeah, right before the exam. Okay, so that makes sense. The next break we get is spring break. Which is near, what is that, the end of March, I think. We've got to run the race till then. I don't remember what happened last week at all. I'm going to blame the drugs. We did Newton's laws, right? We did chapter 5 last week. We did chapter 4 the week before that. We were doing orbital calculations. And so what does this unit consist of? It consists of Newton's laws. 1, 2, 3, right? And that's the free body diagrams and objects and forces and vectors. And then there's that circular motion thing that we did in chapter 5, okay, which instead it still involved forces and stuff, but it's a very specific kind of acceleration, which gave rise to orbits, gravity, Newton's universal law of gravitation. So I always think of 4 and 5. Chapters 4 and 5 are just, to me, they're just one big hole, right? They're just Newton torturing me over and over and over again. Chapter 6 is a different toolbox. And we did a toolbox, we had the toolbox of kinematics in our first unit. And that was kind of nice because really there were only 4 equations for everything, right? And now the toolbox of Newton's laws isn't so much a toolbox as it is Amazon, right? Like you go searching for the tools that you need, and Newton's second law sort of spits out the toolbox on the fly because you have to develop the tools as you go. Maybe it's more like a 3D printer, right? You can get an infinite number of tools out of it, but it starts with one instruction, ma equals f. What we're going to do this week is we are going to take a look at everything we've done before, from kinematics all the way through Newton's laws, circles, everything, but we're going to do it from the point of view of something called energy and this principle called conservation of energy. This is going to get a little bit convoluted today because we're going to spend a lot of our time on something called work. Which sounds a lot like energy and shares the same unit, but is a slightly different idea. We'll get to the energy in a little bit. Do you remember when I asked you what's mass? Like, what is mass? And we were kind of struggling, right? And it was a little bit like, what does salt taste like? We know what it is. We work against our mass all the time, but we lack the words to sort of define it. Energy is a little bit the same way. Let's do this exercise right now. What kinds of energy are there? Name an example of a kind of energy. Kinetic. Potential. Electric. Solar. Thermal. Chemical. Like we can name off different kinds of energy, right? But when it comes to like really identifying what is energy, we struggle, which is why I love Mr. Hewitt's, Paul Hewitt's definition. He teaches at City College San Francisco. Because I heard this once and I was like, that's it right there, okay? And so when you're sort of struggling, like, what's this whole energy thing? Why are we doing it? What's it for? I don't understand. Try to remember, right, that energy doesn't always, can get things going places. Energy is the reason, right? Things can move. So there's a concept, we call it conservation in physics, and this concept of like conservation of energy, we also have conservation of charge, we have conservation of momentum. When we drop that line, conservation, we're not talking about save the planet and turn the lights off and go hug all the trees, which I'm for all of those things. We're talking about a fundamental principle of how our universe is put together. Near as we can tell in all of our observations and all of our work, the amount of energy in our universe has not changed through time and won't change in the future. That's what we mean by conservation of energy. You can't make energy. And you're like, well, Mr. Balogh, what do power plants do? They don't make energy. What does a power plant do? It changes the kind of energy that is in play. A power plant, say up in the mountains, like Millerton, right? That power plant trades the gravitational potential energy of the water stored in Millerton Lake, and as it drops over the dam, they can run turbines that turn that potential energy into electrical energy. A power plant that runs off of natural gas burns natural gas in order to make electrical energy. So it takes the chemical energy in natural gas and turns it into electrical energy. The potential energy stored in your body, the biological energy that comes from the calories of the food that you ate, gets stored, goes through this complex process of, what is it, ATP and, what's the other one, ADP? It was a long time ago, right? Okay. And eventually turns into some kind of motion. Look, this is breakfast happening before your eyes, right? Okay. So we don't make energy. We don't destroy energy. What we do is we keep it the same. No matter what, the amount of energy stays the same before and after. What we're going to do is we're going to trade types of energy. We're going to trade forms. So if you've ever encountered this before, one way of stating this would be to say that. Okay? This is actually not the way we're going to write conservation of energy in the long run. We'll get there. Okay? But in a very simple, overarching idea, no matter what happens, I have to end up with the same amount of energy that I started with, which can be rather confusing, right? Because I can take this tennis ball and I can drop it, right? And if I take a look at the energy the ball has right now, which is not kinetic energy. Why is it not kinetic? Good. We can finally say it's not moving, right? Okay, right? So it's not moving, has no kinetic, so it must have potential energy. It's the only other kind of energy that's not kinetic, right? So chemical energy is potential energy, electrical energy is potential energy. Those are all potential energies. If I let go, right, it changes that potential energy into kinetic energy, right? And if I let it just kind of go, It's not moving anymore. Didn't I just lose energy? I had potential here, and as it dropped, it lost potential energy, got turned into kinetic, and then the kinetic disappeared. Where'd it go? It went into sound and friction and heat and a lot of other forms. We're going to start really simple with this idea, which can be a little bit confusing. Because what we're going to do is we're going to ignore heat and sound and things like, right? And we're going to kind of narrowly define what we mean when we apply conservation of energy. As an example, we'll define the potential energy here, and then we're going to talk about the kinetic energy it has right before it hits the floor. Because before it hits the floor, we don't have to worry about friction or sound energy or whatever, right? Okay. Oh, and by the way, we're finally going to be able to do not free fall, but we're going to be able to do friction in the air because of energy. But we'll get there. We'll get there. But you can sort of conceive of it like this, even though, and I'll show you the end right here at the beginning, what we're going to do is we're going to write it like this. This will be the way that we are going to write conservation of energy. Now, there's a funny term right there, WNC. That stands for work non-conservative. And we're going to get into work and what conservative, non-conservative, all that stuff means, okay? But the one at the top and the one that I boxed are almost the same. In fact, you can get them to be the same if your work is 0. What happens if work is 0 in this boxed equation? And what happens if I move the initial energy over? We get right back to the thing I started with at the top, right? But we need to tackle this whole work idea and see how it relates to changes in energy and so on and so forth. This is going to give rise to kinetic energy, potential energy, all the different types of energy. But I just kind of wanted you to grasp an overall idea of where we're trying to get. The thing in the box will be the one that we apply over and over and over again. It's going to be our template. It's really, it's like Newton's second law in the sense that it's going to generate equations for us, but this generation is a lot more straightforward than Newton's second law. Hint, energy. Is it a vector, scalar, or elephant? It's a scalar. It has no direction. Energy is just energy, okay? Which already makes it good in my book because that means no vectors. Vectors are bad, right? You're welcome, by the way. You guys got to skip last week's lab. Last week's lab was nothing but 3 hours of vector hell. So you can thank my neck for that one. Yeah, we're not going to do it. These poor people. What do you think they're doing? Are they pushing a car up a hill, or are they preventing the car from going down the hill? Or are they slowly allowing the car to come down the hill?
Perception.
Yeah. Okay. This sort of underscores an idea when it comes to work. Okay. Work is force times distance. Now, I know work has a lot of connotations in your life. It's the thing you either try to avoid or the thing that you do so you can eat or whatever, right? Okay. There's hard work, there's easy work, whatever, okay? But in a mechanical sense, in a physics, science sense, work is force times the distance that that force acted. If these people are merely holding this car in place, are they doing any mechanical work?
Yes.
No. If they're just holding it in place, what's missing? The distance traveled. Forces are being applied, right? But no distance is happening because of those forces. Now, if they were pushing it up the hill, would mechanical work be done? Yes. If it was being slowly lowered down the hill, would mechanical work be done? Yes, because there's this distance, there's this change, right? Something's moving. In a mechanical physics sense, work requires not just force to be applied, but that force has to cause something to move over a distance. We're going to write all this down mathematically, but I want you to try and get this idea in your head. So some of you said yes. If I'm leaning here, does this require energy? Yes, it does. Is any work being done? No. Okay? Biologically, are my muscles expending energy to maintain this posture? Yes. Right? We are not talking about that. Okay? Right? We're talking strictly about the fact that, yes, forces are applied, but no distance, no movement is taking place. So no mechanical work is being done. If I'm just standing here, is any work being done? No. In order to do work, what has to happen? So was there friction between my feet and the floor just standing here?
Yes.
Yeah. But is that friction doing any work if I don't move? No. In order for the friction between the floor and my feet to do work, there has to be some sort of distance.
When you step, you say that there is friction between your feet. Or when you don't do anything, there's friction between your feet. But when you move, that's when the friction is. Is that what causes the thermal change and
What kind of friction exists between your feet and the floor when you walk? Static. How do you know it's static? We went over this. When you step, what are the surfaces doing? Step, move. What did my foot not do? Move relative to the surface, right? Okay. So, what kind of friction exists there? Static friction. Okay. Static friction does not cause any of the thermal energy loss. Kinetic friction does. Okay. That rubbing, right? Okay. You can feel the heat if you rub your hands together. That's kinetic friction, and that does cause energy losses. Now, guys, that brings up a good point. The term energy loss, right, or energy gain. Can you lose energy? Energy is always conserved. This is one of those things like, we were talking before class started. English is dumb because it uses a lot of phrasing and terminology that doesn't make sense. And one of those things that makes me mad is energy crisis. You guys heard about the energy crisis? What's the energy crisis? Electricity prices are going up. That's a crisis. You can thank AI for that one. What's the energy crisis?
entropy?
Okay. It's not energy. It's entropy. Okay? Because the amount of energy in the universe, the amount of energy on Earth, the amount of energy in the sun is a set amount. You can't lose it. What you can lose are easy to use forms of it. Gasoline is an extremely easy form of energy for us to use in our modern society. All of our modern processes, from automobiles to automation to factories, rely on this conversion of chemical energy into other forms of energy. We've gotten pretty good at it. It could be a lot more efficient than it currently is, and there's lots of arguments to be made there. But the whole idea of losing energy isn't really right. But a physicist and an engineer will say energy has been lost. And what we mean by that is it went to something we don't want to keep track of. In our case, in this class, we're going to say energy gets lost to friction. We don't want to have to keep track of the thermal energy that doesn't come to the last unit, okay, right now. But we can say that the energy went away. For example, you're driving your car, right? Going 30 miles an hour, right? Light turns red, you hit the brakes. Does your car have any energy while it's moving? Yeah, what kind? Kinetic, right? And then it comes to a stop. What happened to the kinetic energy? It was lost to heat. It got turned into heat through the force of kinetic friction. Okay? So an engineer would talk about the energy being lost. The car's energy gets lost. What they mean is the kinetic energy is turning into a type of energy that we're just not going to worry about figuring out. It's lost to our system, which is the car, right? But universally, you can't make it or destroy it. I mean, force times distance. What's hard, right? Well, unfortunately, physicists have to come along and complicate things, right? Your book writes it like this, okay? So that's how your book writes it. This is how I write it, okay? And you're like, but Mr. Balogh, where'd the angle go? Sometimes textbooks make choices and I don't understand their choices. Let's say that this was a box that is being pulled across the floor. Maybe this is a wagon or a piece of luggage. It doesn't matter, right? Something is pulling this object across the floor, and the object is sliding, right, a distance d. Like it starts here, it ends here, right? This force has pieces. Thought you said there were no vectors, Mr. Balogh. Well, there aren't, but we gotta get through vectors to get to the promised land on the other side. Which of those two components, the x or y component, is doing work? The x. Why the x? It's the same direction as the displacement, as the distance. Okay? The idea here, the idea that I would prefer that you have lodged in your head, is you take the component of force that is parallel to the distance. So if you have a force being applied, but the object's going a different direction, just find the component of force that points in the same direction, you're done. And that could be sine or cosine depending on how you set up your diagram. The F cosine theta times d is kind of hard coding this idea that your angle will always be the way I've drawn it on here. I mean, obviously, like here it works out, doesn't it? This fx is going to be f cosine theta. Why is it going to be f cosine theta? It's touching the angle, right? But what if the angle, and they'll try to do this to you, like what if the angle's up there? Well, this is sine alpha, right? So you either have to learn, okay, well, I've got to go find the angle between the vectors, or just use a skill that you should already be developing anyway, right? Which is find the component, the piece of the force that points in the same direction as the displacement. So that's not the only force, of course, that's working on this box, right? This box, it has a normal force, it has weight, it's got the pulling force, and it probably has friction as it slides, right? How much work is the normal force doing if the distance is horizontal? Zero. It's not doing any work at all. So the normal force, the work due to the normal force is zero. What's the work due to the weight? Zero, because again, it's perpendicular to the distance, right? The work due to the force is force cosine theta times s. Now, I like d for distance. S is an old-timey way of doing a generic distance. Your book uses s. I should probably be more consistent about that. And then what would the work due to friction be? Well, it would be, well, it's not zero because it's parallel with d in a sense, isn't it? Here's the horizontal, and that friction's lying along it, right? Okay. So it's going to be F cosine theta times the distance traveled. The only problem is, what's the angle between the kinetic friction here and the distance? Yeah. Kinetic friction does negative work. So let's go back to our car, right? If kinetic friction does negative work, and to be clear, I'm talking about the kinetic friction between the brake pads and the brake mechanism of your car. Because you want your car to have what kind of friction between the tires and the road? Static, right? But there's kinetic friction between the brake pads and the brake discs. That's the part that's slowing your car down. So we have kinetic energy here as we're moving with our car. We hit the brakes and we slow down, and the kinetic friction does negative work. Why does it do negative work? It's working to take energy away, right? It's working against the kinetic energy that the car already had. So that, you'll see me throw down a minus sign a lot of times. I like the work here is negative. What I'm trying to say is it's doing work opposite what the object's trying to do. So let's do another example. If I take this ball and I throw it into the air, okay, I want you to tell me on the way up, the work done by gravity, is it positive or negative? Why is it negative? Okay, we'll get back to that. I'm going to take the ball and I'm just going to drop it. Positive or negative work done by gravity? Positive. Okay, why is it positive? Which way is the force? Which way is it moving? That's positive work. You notice how positive work caused it to speed up? Right? But on the way up, if I throw it, is it speeding up or slowing down? It's slowing down. That's a clue right there that we've got negative work going on. But let's prove it. Which way is the force of gravity? Down. Which way is the ball going? Negative work. Right? The force and the direction it was moving were opposite each other.
So when they're going in the same direction,
then it's positive. And if you've got any kind of opposite direction, force and displacement, then it's negative.
when you had W for force, is that capital F cosine?
Yeah, that was the pulling force up there. And the S is distance.
The S is distance?
Yeah, that's how your book does it. I like D because distance. I'm using both so that you guys are both confused and I can assert dominance over you. And also so that you get used to seeing different things, right? It's not actually the symbols that matter. It's the context. If you see a force and a distance next to each other, regardless of what symbol is being used, then you know that's work. Let's do a quiz. We're going to rapid fire the mathematical expressions for the different kinds of energy that we have. And then we're going to try and put this all together into one thing. I should just, because I forgot to do it at the beginning, let's talk units. Right? Energy. Energy has units of joules. Okay, and this one is funky because, well, I mean, work. Remember our initial statement, right? Oops, other way around, Mr. Balogh. Energy final minus energy initial. What units does work have if joules is over here? If this is a joule minus a joule, what's over here? It has to be a joule. So work and energy share the same unit. We also know that work is force times distance, cosine of the angle, right? So what's the unit of force? It's a Newton. What's the unit of distance? A meter. So what's a joule? It's a Newton times a meter. Okay? Yeah, we do use capital J as the symbol, but a joule is a Newton times a meter. But what's a joule? It doesn't make, okay? So if you turn the page, like a physical page of your notes, okay, or a textbook or something like that, okay, then that's about a millijoule or 1/1000th of a joule. On the other side, so that's like kind of the small side, the United States uses approximately 10 to the 21 joules of energy every year. So that's a really big number, which again, didn't help you at all because what the heck is 10 to the 21? It's a billion million joules. Help me out here, Mr. Balogh. What the heck is a joule? You're probably more familiar with calories. Calories is an energy unit. When we get to thermodynamics, we'll discover that the calorie isn't the calorie because there's a dietary calorie and a scientific calorie. But 1 calorie is about 4 joules. It's like 4.186. So I just kind of remember that, if I have 1,000 calories, right, then I've got about 4,000 joules worth of energy on my hands, okay? And that's not 1,000 dietary calories. It's 1,000 scientific. What's the difference between a dietary and a scientific calorie? Good. 10 to the 3. A dietary calorie is 1,000 scientific calories. We'll get there later. But a calorie is another unit of energy. Okay? We use joules in here because it's the SI unit. Another form of energy that you might be familiar with if you have ever paid an electricity bill is the kilowatt hour. It's not a kilowatt per hour, it's a kilowatt times an hour, and we'll talk a little bit later about power. But that's another unit of energy. And I can never remember what the equivalent number of joules is. It's thousands of joules. A light bulb. Okay, if you go buy an LED light bulb from the store to put in something, and it says it uses 10 watts. A watt is a joule per second. So a 10-watt light bulb, LED light bulb, is using 10 joules every second to create that amount of light. Okay, so that just, I don't know if that helps you sort of get an idea. I admit I do not have an intuitive sense of like how many joules something is. I usually have to convert to like kilowatt hours or calories or something to get like a more, because like I know what 185 dietary calories looks like. It looks like a Snickers bar, right? That's 185,000 scientific calories, which is almost 800,000 joules, right? So I do have to kind of run those conversions in my head if I really want to know what a joule is. Otherwise, just remember that the units of joules, if you're dealing with energy, no matter what the energy is, it's going to come out in joules. Case in point, kinetic energy, the energy that is associated with the motion of any object, is 1/2 times m times v squared. What unit do we use for the mass? Kilograms. What do we use for velocity? Meters per second. So a kilogram meter squared per second squared happens to be a joule. You might just want to give up on units at this point. Not give up on units, but give up on like trying to break down units and get the units to work out. Remember, if you use standard units for everything, kilograms, meters, seconds, you're guaranteed to get the correct unit out, right? So I know that if I put the mass in kilograms and the speed in meters per second, I will get joules out of this because our toolbox equations, they know how to deal with the units. It's built in to the equations themselves. How do you know when something doesn't have kinetic energy? If the velocity is 0, right? It's not going to have any kinetic energy. All right. Potential energy. This one's a little bit more complicated. It's not going to look complicated. Okay? I'm actually going to show you where this one comes from, even though kinetic energy comes from a kind of a neat place, but we don't have time. Let me show you where it comes from, and then I'm going to make some comments that we're going to have to use later in this course. Because potential energy is going to keep growing. We're going to keep getting different kinds of potential energy as we go. So what we're going to do right now is we're going to do the potential energy due to gravity. Okay? Now, gravity exerts a force on all objects, doesn't it? Okay? So if I've got an object, I don't know what it is, and it's falling, sure, why not? Okay? The force due to gravity on it will be its mass times little g, right? So that's our force, right? It's our weight. And if it falls through a height h, right? Maybe a height above the ground or something like that, okay? And I know you guys are like, well, height, that goes up, Mr. Bailey. Well, it can go up or down, okay? It's just sometimes we use that vertical distance something moves. We just use h instead of d or s or x or anything else, y, okay? So if the force is mg and the distance is h, then the work done by gravity, which is force cosine theta times the distance. The distance is, we'll just say it's down, okay? And the force is down, so what's the angle between these two things? If they're both pointed down, what's the angle? 0, and it's going to end up positive, right? The angle is going to be 0 because they're parallel. So this just becomes a positive 1, right? What's the force? Well, it's mg. And what's the distance? H. There's the work that is done by gravity when something falls through a height h. We call this thing mgh, we call that the potential energy due to gravity. So if I grab my tennis ball, right, and I hold it here, how much kinetic energy does it have? 0. Why? It's not moving. How much work could gravity do if I let go? mgh. Right? Because if I let go, gravity will do mgh, amount of work. And so work is not happening if I just hold it here. Why is work not happening? Well, the net force is 0 on it, number 1. But work can't happen if there's no displacement, right? There's got to be movement, right? So no work is being done on the ball, right? And so, but I know how much work can be done on the ball. We call that the potential energy. How are we doing? Is potential energy work? No, because work is what? Distance, right? Work requires something moving, doesn't it? Okay. But is the amount of work that can be done and the amount of potential energy the same thing? Yes. Work and energy share the same unit. They are different expressions of the energy that the object has. So I'm just going to make up some numbers. We're not going to do any calculation. I'm just going to make up some numbers. Let's say that the ball up here, I'm going to try to hold this ball exactly the same distance above the table as the distance is from the ground to the table. Let's say the ball has 10 joules of potential energy right here. Okay? Potential energy always needs a reference. It has 10 joules of potential energy with respect to the floor. The distance, whatever this height is, right? So let me draw this on the screen. I've got a table, right? And I've got the ball held up here, right? And I'm saying that I got this height right here, right? And the height above and the height below are exactly the same, but this whole height, right? Now if I say it has 10 joules of energy up here, let's figure out what the change in potential energy is. So change in potential energy, delta change in potential energy, is going to be the potential energy final minus the potential energy initial, right? Because that's what deltas mean. Okay, so how much does it start with? 10. And if I let it fall and it gets to the floor, what's its energy down there? 0. Why is it 0? Yeah, the height down here is 0, right? So what's the change in potential energy? Well, the final is 0. The initial is 10. So what's the change in potential energy? Negative 10 joules. What happens if I change where 0 is? This was where 0 was. What if instead I say 0 is at the table height? Now it has 5 joules of energy. We cut the height in half, didn't we? Okay. But energy must be conserved, and the total amount of energy must stay the same. So what does that mean the floor is? Lava. The total amount is 10, right? From where the ball is to where the floor is. I've just changed where 0 is. So what is the floor? If the top got cut in half, where'd the other half of the energy go? We're below 0. So can things have negative potential energy? Yeah, it depends on where 0 is. What's the change in energy here? What's our final energy? Not 0. Negative 5. Minus, and what's our initial energy? Plus 5. What's minus 5 minus 5? It's still the same. What if I put 0 up here? That would make down here negative 10. And my change in potential energy, my final, negative 10. My initial, 0. What stayed the same? No matter where I put 0, what stayed the same? The change in energy stayed the same. Energy must be conserved. Our choice of 0 will determine how easy the numbers are to deal with. It's probably easier to start at 10 and go to 0 and say negative 10, right? Than it is to go negative 5 minus 5, or think about like what could negative energy be. Think of negative energy as like being in a hole, right? If you've fallen in a hole, you have negative energy because you're going to require energy to get out of the hole, right? But 0, where we get to pick where 0 is. We just need to figure out ways to pick it. Easily, yeah, like to be the easiest to use, the most convenient, all that kind of stuff. And I'll give you some tricks for that. But the neat thing is no matter where we pick 0, we can put 0 on the moon if we wanted to. We will always get the same change in energy. So we're always going to be looking at changes because changes are invariant. Other thing to notice. The change in energy, the change in potential energy was negative, right? We keep getting negative 10 no matter where we choose 0. But what kind of work, positive or negative, did gravity do? Did positive work. This is something that will come back in physics 2b, but work and changes in potential energy are always opposites each other. If your change in potential energy was positive, then negative work was done, and vice versa. If positive work is done, then there was a negative change in potential energy. Not my fault. Take it up with the maker. All right. So we got our potential energy defined. Now let's write down the whole thing. Okay? The whole conservation of energy. From like the first slide, right? It was work, non-conservative, equals energy final minus energy initial. It's a seemingly simple equation that is going to grow as we apply what we've learned about energy. What do I mean by that? Can we ignore the work non-conservative just for now? I'm going to keep punting that one down the road. Let's look at energy final. Objects can have multiple forms of energy in their final state. It could be kinetic, and it could be potential. Or they could both be zero, but it's a mix, right? This energy final is a combination of all the different kinds of energy that can exist. Right now we only have two, kinetic and gravitational potential. We're going to add on the potential energy of a spring or elastic potential energy. We're going to add on thermal or energy of heat. Energy, when you get to 2B, it'll be electrical energy, right? The potential energy comes in a lot of different forms that we can just keep adding to this equation. But for right now, lucky for us, we just have 1/2 mv squared and we have mgh. So what this could turn into is 1/2 mv final squared plus mgh final, right? It's like the whole possibility for what that could be. What about energy initial? The energy an object might start with. Well, again, it's a combination of the initial kinetic and the initial potential energies. I think your book might use a little sub-zero. I didn't check. So again, this can be 1/2 mv initial squared. That's my initial kinetic energy plus mgh initial. Oops. We have to subtract this thing, so we got to be careful. Minus the energy initial. Okay. And then now we're left with this work non-conservative term. Non-conservative and conservative work have nothing to do with their political ideologies. There's an easy way to put this, and then there's a hard way to put this. I'll do the hard way first, and then we'll go easy. Non-conservative work is done by forces that are path dependent. Did that help you fully understand what non-conservative work is? No. Friction, kinetic friction is non-conservative work. How's that? Does that work better? Still a little bit bad? Non-conservative work is anything that isn't gravitational potential energy. So far. As we pick up other forms of potential energy, they will come into what we call conservative work. Most forces that we run into that cause things to speed up and slow down are non-conservative, meaning that they really depend on what's happening and like distances traveled and stuff. The only one that's not, that I can demonstrate for you right now as a purely conservative force is gravity. Gravity doesn't care what the path is. In other words, if I take this ball and I just drop it, the amount of work done by gravity is exactly the same as if I throw it sideways. Do you remember how we did those examples where something was launched sideways and something was dropped sideways and they both land at the same time, going the same speed because they were all accelerated the same? That's what we're talking about here. Gravity is a conservative force because it doesn't care if it's just dropped or launched sideways. You're going to get the same amount of work out of gravity. It's path independent. friction is going to be the key thing that we are going to be throwing into this work non-conservative term. Okay? Friction is not something that we can't, it's not gravity, and we can't keep track of it with potential energy. I like to think of work non-conservative as a trash can of this is where I put a force that does work that I don't know how to deal with. What's the only force we know how to deal with so far? Gravity, right? So gravity doesn't go into work non-conservative. But friction would. If they tell you the force that brakes apply to a tire, well, that's non-conservative. If a skateboarder is pushing on their skateboard as they go along, that push is non-conservative. Why? Simple answer. It's not gravity, right? Is the force that a skateboarder exerts gravity? No, right? So if it's not gravity, it's going to go in work non-conservative. If you're pulling on a rope to raise something up, conservative or non-conservative? Non-conservative. Why? It's not gravity. Do you see what's going on here? If I wear a jetpack and I take off, conservative or non-conservative work with the jetpack? It's non-conservative because it's not gravity, right? So try not to get too hung up on being able to identify a conservative or non-conservative force. Treat it more like if it's not gravity, it goes in that work term. Whatever force is being applied, right? So if you're pushing a friend's car that's stalled in the intersection again, right? Okay, is the force you're applying conservative or non-conservative? How do you know? It's not gravity, right? Right now, all we have is gravity and potential energy. But I said what we're going to do is we're going to add kinds of potential energy. So when we finally get to like springs and elastic bands and that kind of stuff, we then will write down some potential energy equations for that. That gets removed. It no longer ends up in non-conservative. It ends up in the conservative side, okay? The side where all the energy terms go. So just try to think of this work non-conservative as the trash bin of put whatever force is causing energy or work over there that's not gravity and anything else we might know along the way. So in the red box is definitely like the whole toolbox. But as you can see, the toolbox like starts spitting out equations, doesn't it? Starts generating all of these different terms. And we've got to come up with a method for getting through, okay? Through the problem-solving process. Like, how do we just really dig in to what's going on? So I'm going to start an example here, and it's an example that we have seen before. It's the hill, it's the mountain, it's the loading ramp, it's the inclined plane, right? It takes care of just about anything that's sliding down a hill. So a loading ramp is a hill, is a bobsled, is the downhill skiing in the Olympics. Like it's all that, right? And of course, a lot more complicated things going on, and we'll get to those complicated things. But let's just, since I mentioned skiing, let's talk about skiing. A skier is going to ski down a hill. Let's find the coefficient of friction. Is that what I did in my example? Yeah. Let's find the coefficient of friction between the skier's skis and the snow. First of all, is there friction in skiing? Yeah, it's why they don't speed up infinitely fast, right? Okay. So there's a limit between like how fast they can go because of the friction that's being applied to them. Air friction, ski friction. We're actually going to find kind of the total friction on the skier, okay? All right. How did we do this when we did Newton's second law? Can we sketch that out just real quickly? Like Newton's second law, We had a normal force. We had the weight. We had the friction going up. And then we had to tilt our coordinate system. Do you remember all this? We had to write down Newton's second law, sum of the forces, and then MA equal, MA equal, Just go back and look at your notes, right? It's bad. And that would only get us, well, that would give us an equation that had the coefficient of friction in it, because remember how fun this is. But we'd have to know the acceleration of the skier. And the only way to find the acceleration of the skier would be to know how fast they're going at the start of their run and how fast they're going at the bottom, and then doing kinematics to find the acceleration, to find the coefficient. It's a lot of work, pun intended. Okay? Not the mechanical kind, the brainy kind. So let's do it from the point of view of conservation of energy. Let's see how using a different paradigm and a different approach can help us understand what's going on, hopefully simpler. We'll see, right? Okay. What you do is you start your visualization. You can draw a picture if you want. You start with the master equation. Like your visualization and your strategy start in the same place. Work non-conservative equals energy final minus energy initial. And we're going to use this as a template to help us ask the right questions for moving through and doing the problem solving. Let's skip one. I always leave work for the end. I like to jump right into energy first. To be able to even talk about energy at the bottom of the hill or versus energy, say, at the top of the hill, or whatever the initial and final, I have to define what the initial and final states are. Like I have to say, like, where is the skier and what is the skier doing initially? Where is the skier and what is the skier doing at the final point? Like, if I don't define what those are, I can't get any traction into this. So as part of your visualization, you're going to pick 3 things. Initial point, final point, and where 0 is. Those are the 3 things you have to pick. If you come to me, Mr. Bale, I'm lost in this problem, I don't know what to do, and I ask you, okay, what are your 3 choices? And you look at me blankly, I'll be like, okay, we got to start with the 3 choices. Because you really can't do anything until you have those 3 ideas down on paper. Okay? Where should we put the initial point? At the top of the hill, the start gate? Okay, great. I like it. So we're going to put the initial point up here at the top. Okay? Where are we going to put the final point? It kind of makes sense, doesn't it? In the context of a problem where you've been given words and numbers and things like that, they'll tell you things like the skier starts at the top of the hill, or maybe the skier starts halfway up the hill, right? Or they'll say the skier has this speed at the bottom. They're giving you information. You want to pick initial and final at places where you know something is happening, like how fast the skier is going at a point, or where you want to find something out. Like one of those 2 choices. You either know something about what's going on, or you're looking for something at that point. Initial and final. That's where you want to pick those things. And this requires a lot of practice and making mistakes and trying and trying and trying. The other thing you're going to put is 0. What I do for safety, and because my brain doesn't like thinking about negative work, I like to put 0 at the lowest point in the problem. This is not necessarily the same as your final position. In this problem, it is. I just put 0 at the lowest point the object makes. So like if it were a roller coaster and the object were doing loop-de-loop like that, right? And I'm just comparing like where it started with the top of the loop-de-loop, I'd still put 0 down here. Just that's just me, right? That's how I do it. You can put 0 anywhere and still get the correct answer as long as you are consistent with your choice. By putting 0 at the lowest point in the problem, I'm guaranteed that all of my heights will be positive. That's kind of what I'm going for, right? I don't want to have to think about negative heights. At least I don't like thinking about negative heights. Okay. So, as part of your setup, you have to do initial, final, zero. And how do you know where to put those things? Practice, 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 practice. Choose locations where you know something or where you're trying to find something out. Okay, so now you just step through and start asking yourself a bunch of questions. What kind of energy would the skier have at its final position? Probably kinetic, because they're moving at the finish line, right? So 1/2 mv final squared. What else? What other kind of energy could the skier have? Potential. Does the skier have any height at the final position? No, we put 0 there, right? The final height is 0. The final position is at the 0, and so that kind of makes that whole term go away to 0. So there's my energy final. It's a combination. I think about both kinetic and potential. You can ask yourself questions like, is it moving? If the answer is yes, it has kinetic, right? And then you ask yourself, is it at 0? If the answer is no, then it has mgh. And then I'm going to subtract off exactly the same idea, exactly the same questions, but at the initial point. Is the skier moving at the start point? No. Technically in the Olympics, they push themselves off the gate. But we'll just say that they just let go and start sliding. Okay? So why am I going to write 0 here? There's no kinetic energy. You might want to just say kinetic energy initial and then run a 0, like an arrow, like a... This is how I indicate something went to 0, or at least I picked it to be 0, right? It's 0 because, right, the velocity is 0. You might want to give a reason. Future you will look back on this and try to figure out what the heck's going on. You want to leave yourself a lot of notes, right? All right, plus, and then is the potential energy 0? Why not? Yeah, 0's not there, right? Okay. The height is not 0 at this point. Okay. So we took care of the right-hand side. Now we got to take care of the left-hand side. Are there any forces here besides gravity? This is unfortunately the question you have to be able to answer. Yes. What are the other forces? Friction, normal, mental, emotional. Sometimes it really helps to just draw a quick free body diagram. It doesn't have to be really like full, right? But like that idea of normal force, blah, 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 mg, all that kind of stuff, right? Okay. I do like to draw a line that represents the line along which the skier is moving, or the object is moving, because we are going to go a distance, right? Down this slope. Whatever the distance is from here to here, there's our distance, right? Is the normal force, is the normal force doing any work? Normal force is not doing any work. Why is the normal force not doing any work? Perpendicular to the distance, okay? Is mg doing any work? No. Yes, but it doesn't go on the left-hand side. Why? It's straight down. No, because we already dealt with it. Where did we deal with gravity? In the potential energy. It's a conservative force, right? So you don't have to worry about... So normal force does no work because it's perpendicular. mg we've already dealt with on the right-hand side. So what's the only one that's left? The friction, right? So the work done by kinetic friction, let's do it in black, will be the force of kinetic friction times the distance that it traveled times the cosine of the angle between those two things. Which way is the distance going? Up or down the slope? Down. Which way is the kinetic friction pointed? So what's cosine theta going to turn into? Negative sine, right? 180 degrees. So this is negative F kinetic times distance equals all of that. Usually, I won't write down this FD cosine theta thing. It just bugs me. Usually what I write, because the non-conservative work is going to be almost always this friction, right? I said that wrong. When kinetic friction is involved, you will always write down minus force times distance. Why minus? What does kinetic friction always do? Acts opposite the direction of motion. Static friction can go with it, right? So if this skier was wearing a jetpack on its back, right? We would actually add a term, force of jetpack times distance, right? Okay. So positive work can go on there, negative work can go on there. What you do on the left-hand side is you add up all the work in the problem. And on Thursday, I'll do an example where we have multiple works going in. Okay. So, what do I have? I have a statement now, right? Okay. Whoops, come here. This line right here, I'm going to clean this up. I'm just going to do, I'm not even going to do math. I'm just going to write down the things that survived from the line above. And I've run out of time. You guys didn't stop me. I was having so much fun. We will pick this up on Thursday. I'll see you tomorrow for Newton's second law. We'll brush up all of our forces and Newton's second law, and then we'll come back to this on Thursday. See you then. Blame me if you're late to your next class.